Hello viewers, welcome to Physics with Sanmitra. I am Sanmitra Bhomik and today we are going to discuss about Newton's ring experiment. This experiment is a part of the wave optics series which we are dealing now, and this is about the interference topic, interference of light. And this is a very good arrangement for creating the interference from thin film. I am showing you how. First of all, let's see the arrangement, experimental setup. We have a convex lens and we have a glass slab which is inclined at an angle of 45 degree. Now this glass slab is there is a telescope, I can say, which is kept here, and here there is a plano-convex lens. It is kept like this. There is a plano-convex lens, and now let's see and there is a monochromatic source out here that is kept at the focus of this convex lens. Now what is happening here? Let's see. Now this monochromatic source is emitting the rays. See, since it is at the focus, so the rays will be parallel after emerging out from the lens. So the part of the rays get reflected. Since it is 45 degree, it will go straight down. It is going down. Now again from here, another part will be reflected upwards, showing in different color, like this. I hope now it is clear. Now we are observing it in there is a telescope. We are observing it in the telescope. Now exactly why we are making such an arrangement? Let's see. We will be focusing only on this part. Okay. Let's draw it separately, this plano-convex lens. See. Just let me see the ray which was falling here. Since it is falling almost vertically, so I is equal to 0, the angle of incidence is 0, and angle of refraction is also 0. Now since it will go like this straight. Now from here, see, there is an angle, so there will be an angle of refraction like this. Then there will be reflection, then there will be refraction. Okay. Now directly from here also there will be some reflection. Now see, this orange ray and this blue ray and this green ray, these two will be interfering. These two will be interfering, and that is just almost similar or almost same as that of the thin film interference which we studied earlier. And in thin film interference there was something mu. There was the refractive index of the film, that was mu, but here this is air, so my mu will be 1. I think this much is clear. Now what we have to do here is that, let's see, our path difference for reflected ray, for reflected ray, our path difference was 2 mu t cos r, 2 mu t cos r plus lambda by 2. This plus lambda by 2, this term is for the additional lambda by 2 path difference that is created due to the reflection. Okay. Now here what I am getting here, see, mu is equal to 1 and r is equal to 0 since I is 0 almost. Therefore I will get delta x is equal to 2t plus lambda by 2. Now we know, let me remove this, let me write again, delta x is equal to 2t plus lambda by 2. Now we know that for bright fringe, let's start with the dark, I'll tell you why. Let's start dark fringe. What we get, delta x is equal to 2n plus 1 lambda by 2. So delta x will be or rather directly 2t will be 2t plus lambda by 2, that is 2n plus 1 lambda by 2, and this lambda by 2 and this lambda by 2 will cancel out, and then only 2n lambda by 2 will remain. Should not cancel like this. Then I can write actually this lambda by 2 and this lambda by 2 into 1 will cancel out, so 2n lambda by 2 will remain, and this 2 and 2 will cancel out, and my t will become n into lambda by 2. T I am getting as n by 2 into lambda. This is for dark fringe. Now for bright fringe, what is happening? For bright fringe, delta x is equal to 2t plus lambda by 2, that is 2n lambda by 2. So 2t will be 2n minus 1 lambda by 2. So t will be 2n minus 1 lambda by 4. So this is the condition for bright fringe. Now let's see one thing here. At t is equal to 0, at t is equal to 0, what do I exactly mean by t is equal to 0? This is my t, this is the thickness of the fringe. When it is 0, at t is equal, at the center, at center t is equal to 0, what I am getting, delta x is equal to 2 into 0 plus lambda by 2 is equal to lambda by 2. So delta x is an odd multiple of lambda by 2, 2n plus 1 lambda by 2, where n is equal to 0. So at the center we are getting a dark fringe. So my fringe pattern will be something like this. At the center we'll be getting a dark fringe, then like this. So let me draw it here. Center there is dark, like this. Now how this spacing will be affecting this spacing, that we will discuss later. We'll discuss it later. Now let me derive some more. This is the plano convex lens, and let me complete this one. And now let's see here. Let's take a section like this. This is T, this is thickness, this is R, this is total is R, so this much I can say, that is R minus T. And let's say the radius C, the ring is forming like this. So the radius of the ring, this one, I can say it will be smaller. It will be smaller. So geometrically, these three R minus T and R become smaller from the right angle triangle. So we can write R square is equal to R minus T whole square plus small r square. So if I solve it, I will get R square is equal to R square. I'm taking R minus T whole square in the right hand side. R square minus 2RT plus smaller plus T square. This will cancel out and R square will become T square minus 2RT. Or rather minus T square plus 2RT. Now we know that T is very small. So since there is R square minus T square, R square plus T square, since it is added with the term that is R, and R is relatively larger, so I can say I can neglect T square almost equal to 0. So I can write R square is equal to 2RT. R square is equal to 2RT, or if I remove this one now, I can write here the expression of R, or rather Rn, that is for the nth one. Expression of T we can write, T we can replace by R square radius square by 2R, radius square by 2R. Now we can replace, or we can add an n here, n. Why n? Because of, or Tn, we can add an n here because the rings are discrete. We are talking about the nth ring. Now what we had for dark fringe, we had 2t, that was the path difference, plus lambda by 2 was 2n plus 1 lambda by 2, and we had 2t is equal to n lambda. We can replace this t by r square by 2r, 2 into rn square by 2 into capital R into t is equal to n lambda. Now this 2 and 2 will cancel out. This Rn we can do, that is dn by 2, that is the diameter by 2. So we can replace it by dn squared by 4r t is equal to n lambda. So now we can write here dn, that is the diameter, that will be, for dark fringe the diameter will be okay, this t will not be there because we replace this t only. Okay, so 2rn square by 2r is equal to n lambda, dn square by 4r is equal to n lambda. So dn will be equal to 4 r n lambda. This 4 we can take out common. Dn will be 2 into root over of n r n lambda, 2 into root over of r n lambda, that is my dn, that is for the dark fringe. It is for dark fringe. Now for the bright fringe, what is the expression for the diameter of the ring? This is the diameter of dark ring, dark fringe ring. So I am just writing dark ring. Now it's the same thing, that is 2t is equal to 2n plus 1 lambda by 2, that is my, or 2n minus 1 lambda by 2, that is my bright fringe. We can derive in a similar fashion. Let's replace 2 into rn squared by 2r is equal to 2n lambda by 2 minus lambda by 2, we can write, or it was not necessary actually. So this is r1 r, this is dn squared by 4r, that will be 2n minus 1 lambda by 2, or we can simply write dn is equal to root over of 2n minus 1 lambda by 2 into 4r, or we can cancel out this one for simplicity and we'll get the expression. Bright rings, actually we used to analyze the dark rings only more in case of Newton's ring experiment, because dark rings are easier to compute. Okay, now let's look at the spacing of the rings. Let's say the dark rings. dn is equal to root over of 2 lambda n r. Let's find out d1. d1 is root over of lambda r. This is d4. Let's take the square. Let's take for n is equal to 1, 1 square, 2 square, that is 3 square, 9, and 4 square, 16. d4 will be 4 lambda r. If I take this 4 outside, it will be, this is d1, so 2 into d1. What is d9? d9 will be 2 into 9 lambda r. So 9 will come out to be 3, that is 3d1, and d16 will be my, similarly, root over of 16 lambda r, 16 will come out to become 4, so 4d1. So d1, d2, d3, d4, all these are forming an AP. So I can say that d16 minus d9, that is d1, d9 minus d4, that is again d1, that is 3d minus 2d1, d4 minus d1, that is again d1. So we can write here, that is dn plus 1 square minus dn square, that is actually d1. So the difference between the ring 1 to 4, that is same as the difference between the rings 4 to 9 and that is same as difference between the rings 9 to 16. So now you can understand how the patterns will be arranged. So it will be coming closer to each other, not exact circular, but exactly it will be like this. Now let's look at the application of this setup. The first application is that to find the lambda, that is wavelength of monochromatic source. Let's take the nth dark ring. I told you we use the dark ring because the easier in the computation. The nth dark ring, I can say it is n dn square. Let's take that is the n 4n lambda r. Let's take the n plus mth dark ring. That will be 4 into n plus m lambda into r. Now if I can subtract them and take lambda common, I will get this. Very simple. Lambda will be d of n plus m whole square minus dm whole square divided by 4 into m into r. This m is the difference between the two rings. Okay, let's solve a numerical based on this. The question states that in Newton's ring experiment EXP, the 15th dark ring, that is D15, the diameter, it is given by 0.59 centimeter, and the fifth dark ring, fifth 5, that is given as 0.336 centimeter. Radius of curvature of plano-convex lens, I mean just below which that is happening, plano-convex lens, that is it is given as 100 centimeter, or we can say 1 meter. Find the wavelength of the monochromatic source. So we just solve this one. So lambda I can write dn plus m square minus dn square divided by 4mr. See, n plus m here, that is n plus m is 15 and n is equal to 5. So difference m is 10. Now let's solve this one. dn plus m, what is that? 0.59 square minus 0.336 square centimeter. These are in centimeter divided by, and the centimeter I have to convert in meter. So 10 to the power minus 2, the whole into 10 to the power minus 4. Now it is in meters. 2 into m is 10, into radius is 100 centimeter, that is 1 meter. So if I solve this, I will get my answer as 5880 Armstrong. Okay, this is my one application. Let me show you another application. Another application is finding refractive index. Just see, what I did was that I took a plano-convex lens and there was no medium, but here I am assuming that in between there is a medium whose refractive index is mu. So what we take delta x we took as mu 2 mu t cos r, since it is r, I is 0, so r is also 0, so 2 mu t plus minus lambda by 2. Now this mu we took as 1, but now we will keep it as mu. So if I keep it as mu, then what will be my final expression? See, I am writing d of n plus m dash whole square minus d n dash whole square. That will be my 4mr lambda, that is n plus m minus m. The same thing as the last one, there will be additional term divided by mu, because this lambda will change that time, because we did not take this mu. 2 mu t plus minus lambda is equal to this, so we did not take this. While deriving this, let me show you again. Final expression what we got, that was is equal to 2n plus 1 lambda by 2, and what we could do here is that this mu we can write it here, this lambda by mu. So this lambda by mu, this term, instead of lambda we can write lambda by mu. So this is for the normal case, and this is for the case with the refractive index. And in the air we can also find, that is dn plus n. This is the normal case in air. dn square is equal to 4m r by mu. Now we can just find mu by dn n plus m square minus dn square divided by dn plus m dash square minus dn square. By this formula we can find mu. This is very simple. So that's all for this lecture, and if you like our content, then please subscribe to our channel and click on the bell icon. Thank you.